Okay, good afternoon. Dr. Jensen here. So we are going to look at a few practice problems from some simple gas laws. All right, the first couple of problems here, the first problem is kind of two parts. So in this particular problem, let me, this is common in the first introduction of the gas chapter, because we have just basic pressure units. Throughout the chapter, they use a variety of gas pressures, and so you have to be comfortable with being able to convert back and forth between these various units. Okay, so millimeters of mercury is a common unit that's given, and we want to be able to convert to PSI, or pounds per square inch. Okay. Secondly, we would like to be able to convert to ATM, which is our main pressure unit that we use in chemistry, so the atmosphere. So starting from the unit that we're given, okay, now for PSI, there's not a direct conversion to PSI. So your best bet is, if you're memorizing the pressure units, which you probably need to, is to go to ATM first. There's 760 millimeters of mercury in one ATM, right? And then in one ATM, right, there's 14.7 PSI, right? And so this allows you would multiply all your units on the top, divide by all your units on the bottom. Setting them opposite one another will eliminate the extraneous units, leaving you with only one unit left here at the end. And you end up here with about 12.2 PSI. Okay. Similarly, if we want to go to ATM, starting from the unit we're given, okay, here we have a direct conversion from millimeters of mercury to ATM. So similar to what we did up here, we want to set our unit opposite. So we know there's 760 millimeters of mercury in one ATM. So you're really just dividing by 760 in order to do this conversion. This also is the same unit for torr, if we're doing torr as well. So we get here about 0.31 ATM. Okay, so there's a variety of these kinds of pressure units you have that you may see in a beginning of gas chapter. You have torr, you have millimeters of mercury. You may even see inches of mercury, some US units in there. Obviously PSI, ATM. Depending on how much more complicated they are, there's some things like a bar that's another unit that you may see, but also you have the Pascal, right? And the kilopascal. So generally in general chemistry, you should be able to convert between these at least basic units from one to another, okay? All right, so let's look at a second problem. All right. Now this problem is fairly standard. Okay, so this problem is a fairly standard introduction problem. So in the beginning of the gas chapters, usually they talk about things like Boyle's law or Charles' law and the ideal gas law are considered some of our simple gas laws. So here we have a sample of gas that has an initial volume of 2.8 liters at a pressure of 755 millimeters of mercury. And if the volume is increased to 3.7 liters, what would the pressure be? Okay, so when approaching these problems, the first thing you should think of is conceptually, what do we expect the value to be? Okay, so keeping in mind that they have an inverse relation of pressure and volume. If we apply pressure, okay, if the pressure goes down, right, if we decrease the pressure, we would expect the volume to increase. Okay, likewise, if you increase the pressure, you would expect the volume to go down. Okay, so in this case, it has an initial volume of 2.8 liters, and then it's increasing to 3.7 liters. Okay, so we're increasing our volume from 2.8. Okay, so we're increasing our volume. So if we're increasing our volume, we would expect our pressure to go down, and so our end unit should be less than this value. All right. Okay, so let's make this a little bit bigger here. So the common thing in this, so the equation for where we have a relationship of pressure and volume is similar to this setup. You have P1 V1 equals P2 V2. Okay, and this is often called Boyle's law. All right, this is the mathematical Boyle's law. In here, the pressure units, you just need the values to be the same on both sides. Okay, there's not really a limit here of which units you should use. So if we have 2.8 liters and 3.7 liters, right? Those are our volumes, right? V1 and V2, okay? My initial pressure is 755 millimeters of mercury. Running over my multiplication here. And so you just have a second pressure value. Okay, so the way this works, we're going to multiply and then divide, right? So you're going to divide both sides by the 3.7, right? And that should eliminate and isolate your second pressure. Okay, and so my second pressure here becomes 571 millimeters of mercury, which is less, which is what we expected. Okay, so we should get a smaller number. Okay. All right, let's look at another common gas, simple gas law. Okay. So this was another one where here we're looking at a syringe containing 1.5 milliliters of oxygen is cooled from 95 to 0 degrees Celsius. What is the final volume? Here there is no pressure. So it's keeping pressure constant. Okay, that's the variable that's kept constant here. So it's the relationship of volume and temperature. All right, so this was a function of Charles' law. And so in Charles' law, you have V1 over T1 equals V2 over T2. Okay, now the consideration here for Charles' law was that the temperature has to be in Kelvin. Okay, it has to be in units of Kelvin. All right, so you have to convert these to Kelvin by adding 273, right? And here, again, if you're tackling these kinds of problems, we should be able to look at them, what should we get? And in this case, from Charles' law, if we're looking at volume and temperature, they are linearly related. So as you increase the volume, you also increase the temperature, or vice versa. If the volume decreases, the temperature we expect is also going down. All right, so since we're decreasing the temperature, we're cooling it, okay, we would expect the volume to likewise go down. Okay, so again, here our initial considerations have to be in the temperature range. So okay, so you have to convert both of those to Kelvin. So 273 Kelvin, and then it comes out as 368 Kelvin. Okay. And so when we plug this in, my initial volume is 1.5 milliliters, right? And so it was initially at 368 Kelvin. And so my second volume, again, the volumes can be the same. There's not a limit here. They can be the same unit as long as they are the same. So as long as it's not looking for liters or something. And 273 Kelvin is the second temperature I'm given. Okay. So again, same thing as the Boyle's law. You have little, multiply and divide. And this is how a lot of these units are generally done, is you're generally given 3 out of the 4 terms. And so it ends up being just kind of a plug and chug, multiply and divide kind of solution. So as we divide and then multiply, we isolate our second volume, which here comes out as 1.15 milliliters. So it is less than the 1.5 milliliters as we expected conceptually. Okay. All right. Last one. Look at here. This is looking at a few more conditions. So what is the volume occupied by 0.118 moles of helium at 0.97 atm and 305 Kelvin? So already here, the inclusion of moles should be the trigger here that you're using the ideal gas law. Okay, ideal gas law is important. Okay, so you should know the ideal gas law. Here, the R value is a constant. Okay, R equals 0.08206 liter atm per Kelvin mole. All right, so it is kind of our Rosetta Stone value that allows us to convert back and forth between these various units. All right, so in this case, that means that the temperature must be in Kelvin, okay, and is your moles, right? Your volume must be in liters, okay, and your pressure must be in atm. Okay, so this is how this problem can get complicated, is really just when they give you a hodgepodge of units to start with. So when we have things like degrees Celsius and Pascal and millimeters or microliters and things like that. So when they change up all these temperatures, then you got a little bit of converting to do before you can plug everything into the PV equals nRT. Okay, so here we have our pressure. And we're looking for the volume. We don't have that. We have 0.118 moles times our R constant. All right, I'm not going to write it again. I'm just going to put it in here. Oh, and times our temperature, 305 Kelvin. Okay, and so this is the only term that we're missing, right? And so we just have to rearrange our equation. So, right? So we're just going to bring our pressure over, multiply our top terms, divide by our pressure here. And so my volume comes out to be 3.04 liters. So when it comes out, it will be in liters. Okay, because it's driven by the R value. Okay, kind of the key here that you should be looking for, some things that give away that you need to use the ideal gas law are things like the inclusion of moles. Generally, if there's moles involved, it's a good chance that the ideal gas law is the equation you're going to need to use. Okay. All right, so that is it for our initial gas law chapter problems. So we have simple gas laws, things like Boyle's law, Charles' law, the ideal gas law, and some basic unit conversion that have to be able to be done. And the next video, we'll start looking at some more complicated practice problems, looking at things like partial pressures and some other stoichiometry and things like that.